Hi everyone, welcome to a video in which we talk about binary classification. We're going to talk about different loss functions for binary classification, and we're going to talk about the margin. So in the setting in which we're talking about boosting. We take in this case a different base functions Tm, and we average it, take an average of them with alpha m, and we sum them, and that is our function f of x. In the case of binary classification, we are considering y, our target, to be either 1, plus 1 or minus 1. And then we take our hard prediction with each y hat to be the sign of this f of x, so either plus 1 or minus 1. Okay, and the margin, which is something we are defining right now, is something defined as y times f of x. Okay, so the margin is actually pretty useful, and we have this claim here that says that basically the margin is bigger than 0 if and only if x comma y, this observation x is correctly classified. So let's prove this, right? So so xy is correctly classified. So let's prove this. So suppose that margin is bigger than 0, meaning y times f of x is bigger than 0. So we have here two possibilities. In the possibility y is equal to 1, then that implies that f of x is bigger than 0, and then that implies that y hat, which is the sign of f of x, actually, which is the sign of f of x, that is 1. Okay, so the second option is y equal to minus 1, and that will imply, since the margin is positive, that f of x is less than 0, and that will imply that y hat, which is the sign of f of x, is equal to minus 1. Okay, so basically in both cases we have the observation x to be correctly classified. Okay, now let's go the other way around. Suppose that x is correctly classified. What it means is that y is equal to y hat, right? So if y is equal to 1, y hat is equal to 1, and then that will imply that f of x is bigger than 0, just because the sign of f of x is 1. And that will imply that y times f of x is bigger than 0. So now, if y is equal to minus 1, then y hat is equal to minus 1, and that would imply that f of x is less than 0. So again, the margin, which is y times f of x, is bigger than 0. Okay, now let's talk about the other way around. Suppose that x is correctly classified. Actually, we just did that, so it's never mind. So let's talk about properties of the margin. As we prove, if the margin is bigger than 0, then the observation is classified correctly. If margin is less than 0, the observation is classified incorrectly. The margin is like the residual in kind of for binary classification. So the residual we define in regression. So this margin is kind of like a residual in the following sense. Most of the loss functions for binary classification can be written as a function of the margin. So if you remember, in the case of regression, we most of the time write the loss functions as a function of the residual. Okay, so the margin is kind of like the residual for regression. but for binary classification. Also notice that our function f of x, when f of x equals 0, that is the decision boundary for that model, okay? So let me go ahead, because you probably are asking yourself, well, we don't write the loss function, say for logistic regression, the log loss, we don't write it in terms of the margin, right? So basically what I am going to show you is that we usually basically write logistic regression for the case in which y is either 1 or 0, right? But so you guys haven't seen this written when y is -1 and +1. So basically what I'm gonna show you is that we can rewrite, if we consider y to be -1 and +1 instead of 0 and 1 for logistic regression, then we can write the loss function this other way. So I'm gonna prove that to you. So, and if we are able to do that, you're gonna see that then this loss function is a function of the margin, right? Okay, so let's do that. So the first thing I'm gonna do, I'm gonna start with our loss function, like with this function right here, right? So this function 1 can be written in the following way, and let me know if you guys agree with me here. So what happens if I put like y equal 1 here? So if I put y equal 1, so this part here is equal 0. So we can simplify this to do minus log of y hat. By the way, this will be 1, so I don't have to write it, right? In a similar way, if y is equal to 0, then this part is going to be 0, right? And then this is going to be 1, and we have minus log of 1 minus y hat. Okay? Now, I would like to write all of this in terms of f of x, okay? So let me simplify this formula, and let me basically, first of all, remember that y hat is equal to, it's a sigmoid of f of x, so it's like 1 over 1 minus, plus e to the minus f of x. Okay, so this is just basically our definition here. Okay, so basically minus the log of y hat is equal to the log of 1 plus e to the minus f of x. Okay, so and now if we put like minus the log of 1 minus y hat, well, let's see. So what do we have? We have minus the log of 1 minus 1 over 1 plus e to the minus f of x equal. So let me actually down here write this 1 minus 1 over 1 plus e to the minus f of x. So this is equal to what? This is 1 plus e to the minus f of x, 1 plus e to the minus f of x minus 1. So what we have here is e to the minus f of x divided by 1 plus e to the minus f of x. So now we can multiply by e to the f of x, the numerator and denominator, and we get 1 plus e to the f of x plus 1. Okay, so now if I take the log of this, so that would be right here minus log of 1 over 1 plus e to the f of x that will be equal to the log of 1 plus e to the f of x. Okay, so summarizing, what do we have here? So we have that the loss function L, so L of y f of x, because we have rewritten all of this, is equal to, actually let me add a page here. Add a page. Sorry about this. Okay, so let me actually try to write it down right here. So this is equal to log of 1 plus e to the minus f of x for y equal 1, and is gonna be equal to log to 1 plus e to f of x for y equals 0. So what I can do right now is that I can just, I can basically say, well, instead of saying y equals 0, I'm going to encode the 0 as a y equal to minus 1. And I can just do that. I can say, well, what is the probability for 1 and what is the probability for minus 1? And the probability for minus 1 is going to be 1 minus the probability for 1. And just keep the same loss. So I am just going to erase this and put a minus 1 here. But now, since I have changed the encoding of y, I can rewrite this as log of 1 plus e to the minus y f of x. So think about it. If y is equal to 1, I get a minus 1 here. If y is equal to minus 1, I get a plus 1 there. So hopefully you guys saw that I basically was able to show this formula here. So I was able to rewrite this formula for the case of y equal to minus 1, 2, and 1 as a function of the margin. And you're gonna see why this is gonna become handy. So here is a plot of several loss functions as a function of the margins. So, and the goal of a loss function, if you remember, if you see what we have talked about so far, is that the goal of a loss function should be to penalize negative margins, because negative margins means that the model is incorrectly classifying my observation. So the loss function should be mostly 0 for large positive margins and should be large for large negative margins. So different loss functions are gonna penalize differently, okay? So here we have the logistic regression loss function, we have the SVM loss function, and we have the AdaBoost loss function. So I'm about to show you the formulas in a little bit. So, but you see that the AdaBoost loss function, when is exponential, so it's gonna penalize the large margins in an exponential way, while the logistic regression and the SVM margins are kind of linear on the margin. So again, this is a function on the x-axis we have the margin, on the y-axis we have the loss, and the objective of these loss functions is to penalize the margins. So what is going to happen is that a loss function like AdaBoost that is exponential is going to concentrate, say, too much, maybe in outliers. So suppose that you have a photo of a cat, but actually somebody mislabeled it to be a dog. So that is an outlier, for example, right? So the AdaBoost exponential loss function is going to concentrate on those outliers, and those maybe misclassified examples too much in comparison to an SVM or logistic regression losses. So yeah, so let me actually show you what is the so basically these are the formulas for the exponential loss. Is e to the minus y of f of x. So see that all of them are the function of the margin. They are a function of y times f of x. Then we have the log loss, which is what I just showed you. The log loss just works. This works for any function f of x. It's not just for logistic regression in particular. So this will work for anything. And the hinge loss, which is the function that is used for SVM. So all are these possible loss functions for binary classification. The main point I wanted to make here is that the exponential loss function is gonna most likely concentrate too much in these outliers, and we in most cases prefer using the SVM loss function or the log loss function. Okay, thank you.